You deploy a backend configuration that dynamically returns the exact access control allow origin header required for each request. Yet in production, users encounter intermittent blocks that prevent the application from loading data. The standard response is to rewrite the backend logic, or scrutinize the front-end framework, or disable security protocols in the local development environment to bypass the error. These failures are rarely caused by a bug. They occur because browser security policies are interacting with the invisible barriers of global deployment infrastructure. Managing CORS exclusively through application logic leaves the system vulnerable to the environment it runs in. Stable production routing requires looking past the application layer. The same origin policy is a wall enforced by the browser. CORS acts as a specific negotiated loophole through that wall, but it relies on consistent communication between the client and the server. Enterprise architectures use content delivery networks to reduce latency by distributing payloads across global nodes. A CDN changes the request path. Instead of reaching the server directly, requests stop at a central intermediary. To optimize speed, these nodes cache responses by URL path, stripping away origin metadata and ignoring the security context required for a cross-origin handshake. When dynamic security policies meet these rigid caching layers, the system becomes susceptible to unpredictable failures. If user A requests a resource, the backend attaches a uniquely colored authorization tag. The CDN caches this response, storing user A's header globally. When user B requests that URL, the CDN recognizes the path and bounces back the cached packet without consulting the server. User B receives an HTTP response explicitly stating that only site.a.com is allowed to access the data. The browser detects the mismatch between site.b.com and the cached authorization header. To prevent potential data theft, it hard blocks the request. The backend logic performed correctly, but the CDN served a valid security header to the wrong user. This is the mechanism of cache defacement. The specification-compliant fix for this behavior is the HTTP vary response header. The origin server must attach vary origin to the response payload to change how the CDN handles the data. This forces the CDN to recognize the cache key includes the requesting origin. The single cache block fractures into multiple distinct compartments. Traffic from different domains is now safely routed into isolated buckets, preventing cross-contamination of CORS headers. This creates a performance trade-off. By preventing cache defacement, you reduce the cache hit rate, as the CDN must now store a separate copy of the asset for every unique requesting domain. Enforcing vary origin resolves the errors, but it forces a choice between security integrity and CDN efficiency. Resolving the caching bug does not remove the architectural friction inherent in cross-domain API calls. Browsers restrict cross-origin requests that have the potential to alter server state. This restriction triggers an options pre-flight request before the actual API call can be executed. This adds significant latency. Each interaction requires an extra round trip across the network just to verify permission to communicate. Even when pre-flight responses are cached using access control max age, the requirement remains a constant architectural drag on performance. Optimizing these headers mitigates the damage, but some architectures avoid these penalties by removing the cross-origin boundary entirely. One strategy utilized by enterprise stacks involves removing CORS from the client-server interaction entirely using a reverse proxy. This relies on the fact that the same origin policy is a browser-side mechanism. Server-to-server communication is immune to these restrictions. Implementation involves deploying routing layers, such as Nginx, Cloudflare workers, or Next.js rewrites, at the edge of the front-end deployment. The proxy maps the backend API to a subpath on the front-end's domain. The browser communicates exclusively with a single origin. When a user triggers an action, the reverse proxy intercepts this request internally and tunnels it seamlessly to the hidden backend server. Because the request URL matches the front-end domain, the browser processes it as a standard same-origin request. This removes the bottlenecks. The browser never initiates an options pre-flight, and the server never needs to generate CORS headers. Without dynamic security headers, the CDN can cache paths for all users without the risk of cache contamination. By creating a single, unified origin, reverse proxies decouple application logic from browser security constraints. Systems engineers can evaluate their routing requirements against a specific architectural decision matrix. If you are building a public-facing API for third-party domains outside of your organizational control, you must use CORS headers. In this case, enforcing very origin is required to protect the integrity of the CDN cache. However, if your organization owns both the front-end and the back-end, exposing cross-origin endpoints to the browser introduces unnecessary complexity. Internal ecosystems should default to reverse proxy routing. Modern frameworks frequently build these proxy capabilities into their deployment defaults to simplify the path to production. Efficient CORS management in enterprise environments relies on infrastructure design. By ensuring the browser never sees a cross-origin boundary, the entire class of caching and preflight errors is eliminated.